Welcome back, everybody. Hope you had a great lunch break and you got to chat with a lot of people who are here from different parts of the world. We are ready to resume the rest of the day, and that means we got about 6 more talks to go. Talks, interviews, panel discussions, all of the above. And let's dive right in. So for our next panel, we're going to bring on 4 amazing people. We're going to be covering privacy-enhancing technologies, short-term PET, and we're going to talk about how we can actually make cryptography more applied. This means we're going to cover what the use cases are, what some open problems are, how they're getting addressed, what scale, what time frame they're getting addressed on, and how you can think about using them in real-world applications. So for this, I'd like to bring on our 4 awesome founders. I'll bring on Miguel from Nillion, Ravital from Sunscreen, Remi from Inco, and Pascal from Zama. Please welcome all 4 of them on stage. There's a lot of new ground to cover on this one, because this might be the most sort of with an asterisk technical panel we'll do, which just means we have to just introduce a lot of terminology. But what I'll kind of do is I'll have all of you start with a quick intro, starting with you, Miguel. Just let us know who you are and what you do, and I guess maybe why. That's getting too philosophical. Just stick the first 2.
Okay, just the first one. Hi, everyone. My name is Miguel. I'm the Chief Scientific Officer at Nillion. And essentially, my background is at the intersection between engineering and math. So I have a PhD in math, but also a master's degree in telecom engineering. And over the last 20 years, I've been working on developing and implementing algorithms and protocols on distributed networks.
Hi, I'm Ravital. I'm a cryptographer by heart. Started working in lattice cryptography while I was an undergrad at Berkeley in math. Have stayed in this space since then, and I'm happy to be here.
I'm Remi. I'm the founder of Inco. So previously I was one of the founding members of a DeFi protocol on Polkadot. So we built a Paillier chain. Also a software engineer at Google and Microsoft.
Yeah, and I'm Pascal. Hi, I'm the CTO at Zama, and my background is in cryptography. Been working on FHE, on HE for, what year is this? 2024, for 25 years.
Yeah, amazing. Well, since we opened up that can of worms already, let's kind of talk about what HE is and what FHE is. So maybe I'll kind of go back to you, Pascal. Tell us in a hopefully easy to understand way, what is homomorphic encryption and fully homomorphic encryption?
Yeah. So initially, FHE was a concept that was invented like nearly 50 years ago, but it was just that. It was like a concept for many years. And the concept was, if you look at standard encryption, what can you do with an encrypted data? And the answer was nothing. You can just store it or transmit it along to somebody else. But it's like sending data to the future, right? You're encrypting, you get something that is going to be decrypted later in time, right? But you cannot do anything with the ciphertext. It's just like data. It's not that really. You don't want to get rid of it, but you're sending the data to the future. Right? So the concept of FHE at the time was, what if we could compute over this encrypted data without having to decrypt it? And so at the time, but it was like the 70s, it was the time that modern cryptography suddenly appeared, and people had like these new concepts about public key encryption and obfuscation and plenty of, new ideas. And it was just one more concept, And it took some years before people discovered actually HE, homomorphic encryption. It wasn't fully homomorphic encryption, where you can multiply 2 encrypted values. You do an operation of the encrypted values, and it gives you an encryption of the product of these 2 plaintexts without having to decrypt anything. And irrespective of that, there were also like crypto systems where you could do addition. But there was never a solution that would combine both addition and multiplication. And that was the dream to achieve that. And that is exactly fully homomorphic encryption. And it wasn't until 2009 that Gentry found the first crypto system that actually fulfills, enjoys these 2 properties simultaneously. And that was an eye-opener for a lot of people, including myself, because we've been with like colleagues, cryptographers, we were like trying to prove that it was impossible to build fully homomorphic encryption because it was so hard. It was so hard. So we were figuring out, okay, it's not normal that it's so hard. Probably it's impossible. Let's prove that you cannot build fully homomorphic encryption. But it was also very hard to prove that it was impossible. Now we know why. And so Gentry's crypto system, when it appeared, was stupidly inefficient, but it had the huge merit of answering the question of the existence, right? And since then, I mean, it was like 15 years ago, we've seen a tremendous evolution in the field, and suddenly a lot of people were, attracted by this question, how to improve it, make it efficient. And now we're at a time where we're very proud to see that it's finding its way to production. This is how far we've come, over the course of these 50 years. It's now a reality, and it's very exciting to see that.
That was an amazing overview, and I think that kind of really sets the stage of like how far we've kind of come from just research papers to just mathematically knowing it's possible to now having the compute to actually do all these things. So kind of just jumping on that same theme, I'll kind of go to you, which is, okay, so we know from that paper it's possible, but it's just not as efficient. And now the game is make it efficient and fast. And this is something that you're doing. So what is it that you get to optimize? And what does that look like long-term in terms of how crazy of a scale and efficiency are we thinking, we're talking about, and just what goes into making those decisions?
Yeah, so the challenge really comes that there is a very large gap between what an average engineer who's not a cryptography expert can do versus somebody who is an FHE expert, what performance they can get out of it. There are all kinds of parameters you can play with. You can think through things like security. Do you actually need 128 bits of security for your particular application, especially if it's short-lived? You can think through things like error rate, the depth of the computation, and you can really pull out a lot of performance from that. So from some of our work on FHE compilers, we found there can be 100x, 1000x performance difference between what a non-expert can get versus what an expert can get out of FHE. There is only so much we can do on the algorithmic side. I would say the next frontier really has to do with hardware.
Yeah, we'll get into that too. I want to make sure I cover the intro on most of the panel. So FHE we kind of covered, including HE. You're working on MPC. Tell us, or tell the audience, how does that kind of differ from how people think about cryptography and just overall kind of privacy enhancements that go with it?
Yeah, so FHE, we've been talking about FHE. It's its own thing when you think about a client-server architecture, in that the client has the encryption key and sends the ciphertext to the server performs some pre-processing or some processing and then returns back the ciphertext for decryption. But FHE can also be thresholdized. It can be used so that the private key is shared amongst a number of parties. And it is in that context that FHE now becomes, in a sense, a flavor for building an MPC protocol. An MPC protocol is just a way for a set of parties to perform computations on a function while keeping the inputs secret. And so FHE in that context can be considered as one flavor. And there are more flavors than that. For example, it can be built from garbled circuits, where the idea is that you encode the inputs, but as a difference to FHE, you also encode the circuit itself. And then what you obtain when you run the protocol is an encoding of the outputs, which you collectively decode. And it can also be built, for example, from linear secret sharing. But instead of applying the secret sharing to an encryption key, you actually apply it to the secret directly. And so the parties perform computations. For additions and linear operations, it's easy because those operations are local. But for non-linear operations, it requires some communication. So those three kind of flavors hit different spots on three-dimensional performance cube, where we could look at the number of rounds, so round complexity, the amount of bandwidth that you need to send, which is communication complexity, and then the computational complexity. Each one of those three flavors is hitting a different spot. Each one has like good things, but also an Achilles heel, so to speak.
And also, I mean, none of these are all complementary to each other. You can have multiple ways to communicate, and this is about information sharing, not about necessarily proving some information. So there is not a FHE versus MPC here. So I want to make sure we don't confuse that audience on all this. And lastly, what I want to go to is you, Remi, which is Ravital and Pascal just talked about compiler optimizations for FHE, and you are kind of making it more practical with Inco with an EVM FHE equivalent actual developer environment. So tell us more about like what is possible with Inco right now and kind of how you're thinking about it and what sort of made you make this work with the EVM.
Yeah, maybe just to start, like why we're excited about bringing FHE to blockchains. I think if we really want to use blockchain as this value layer, there needs to be a minimum confidentiality. And this is because, you don't want your neighbors or your colleagues to know how much you're making. You don't want them to know that you have a lot of crypto, which could give you a lot, security risk. We really think that, if we were to zoom out, the reason why public blockchains are transparent is because you need to be able to verify these transactions, right? But it's really more of a bug or just more like a short-term limitation, in my opinion, because the idea is if you can do computation over encrypted data in a verifiable manner, I think this should be the kind of like the natural evolution of this blockchain layer because, like I said earlier, I think not having any confidentiality is actually itself quite difficult for mass adoption in a very practical manner. Now, when you apply FHE to, blockchain or to an EVM, the major benefit that you get is now you can store encrypted data on chain, but not only that, you can also compute on top of it. So if we think about this today, we can only build use cases that make sense on a transparent database today on Ethereum or Polygon or any public blockchains. But this is really not how Web 2 works. What if you want to build, like, let's say a poker game where you have to hide values? What if you want to build like a TOTP that has some kind of secret key that verifies against time, for example? You need to have something confidential on chain to check against. And that itself doesn't necessarily mean it's about privacy. It's just, the way certain applications are built, you need to enable confidentiality on chain. And so this is what we do at Inco with the, EVM that has FHE enabled, is we think that we can allow kind of like the next frontier applications that weren't possible today. And so we do it in two ways. One is people can build on Inco as a modular blockchain. And we also plan on extending confidentiality to existing blockchains, which will have a hard time supporting FHE given certain, hardware requirements. There's also like an NPC component for decryption. So this is where we see kind of like the future or kind of like the next frontier of applications.
Awesome. Well, maybe this is a good time to open up for all of you here. Can we think of other examples to get a better intuition on like why privacy enhancement or just confidentiality is great on chain and applications that will be definitely way more possible that are either hacky or not possible right now?
Well, I think there's some low-hanging fruit. Like for example, you have DAOs. You can do voting. You have like on DeFi, you have encrypted order books, or you can have also auctions, private auctions, or you can have dark pools, or you can have private DEX. You can have as well like the policies associated to transactions. You can have them also in privacy preserving mode. Beyond that, you can have also in like supply chains applications and so on. But there's one we will probably explore more low-hanging fruit. But there's one that I would like to bring the attention to, which is not a low-hanging fruit, but I think it's really important, and I think it's AI. So the way I think it's going is that AI is, of course, going to become smarter and smarter, but it's also going to become personalized. So it's going to learn everything about you, or everything that makes you you. And that's really dangerous. We've seen that already with OpenAI, with this feature that they have unlocked, which is memory. Now they can remember things about you. And of course, when you read the legal text, there is this pinky promise that kind of says, oh, if you tell us, we will delete it and you will never share it. But I think what's at stake here is really sensitive because we're talking about all the emails you've sent and received. We're talking about, the lies you've told to people, the private messages you shared with your partner, like what you really think about your boss, or, a lot of things that you may know and things even that you may not know. Like, for example, you may not know that you're not as smart as you think, or that you're not as funny as you think, or you may not know that you are actually, the way you talk, you're developing already symptoms for Parkinson's or some, mental sickness. So all of this information can destroy a person, really. And so a pinky promise is not going to be enough. We really need privacy-preserving technologies. I think this situation is putting privacy-preserving technologies to the test. So the society actually needs what we are working on here. I think all of the projects are working on private AI and related topics, because this, I think, is fundamental for our society. It's a really important challenge.
Yeah, maybe I guess we spend a lot of time thinking about use cases, kind of like the novel use cases. Personally, I'm very excited about payments generally. So as we all know, stablecoin is one of the killer use cases of crypto. However, in the context of payroll, if everyone is transparent, it's quite inconvenient because everyone within the company knows how much everyone's making. This is sort of a bad practice, non-bad practice in Web2 already. So, just adding a layer of confidentiality to me is a fairly practical use case. The other thing is, oftentimes we think of privacy kind of like against the institution in terms of the blockchain setting. But the other part that a lot of people don't think about is really against each other too. I wouldn't want my friends, my family to know how much I'm making, for example, right? This is the layer of confidentiality that I think maybe a lot of people don't spend enough time thinking about, which, including the payroll use case. Same with private voting, right? Today, if you do a DAO voting, it's completely transparent. And there are repercussions, especially if you're from the core team member or you're somewhat influential. And, in the Web2 world, I know families that, don't talk to each other because they have different political beliefs, right? So, just having some layer of confidentiality on private voting is going to be extremely important for this blockchain system to work. And then lastly, I think, I'm pretty excited about gaming. I grew up playing video games. Today, crypto games are very limited to the ones that make sense on a transparent database. So, something like tic-tac-toe, where it's okay to reveal kind of like your move. But most games that are actually fun require some hidden mechanics, right? So if you want to bluff, right, like a good poker game, or kind of like the Mafia game that we built previously, it's a fully on-chain Mafia game built on Inco, where, you could be a doctor, detective, or killer. That's a hidden role that's generated on-chain, also stored on-chain. But now you can change the game, the dynamics completely, right? So because you can bluff, you can strategize. In other games, you can consume resources, you can spy on people. So these are the more novelty that we think we can bring to the crypto space that just aren't really feasible today or very difficult to achieve. And yeah, so yeah.
No, that's just great, because right now anybody trying the same things ends up going off-chain for that compute and then saying, I did it, but that still relies on some assumption that they were honest. And why have that barrier? And this kind of helps us do this.
Yeah, right. And this is really why I think FHE is very interesting, because it's deterministic, right? So I think in the context of blockchain, I think it's kind of like a very natural suit for this purpose. Yeah.
Maybe the other thing to dig into here will be just kind of actually talking about, for FHE, just compiler optimization. So you said anywhere from 10 to 1,000x improvement could be out there, and possibly more, or with the help of GPUs, that scale or more. What does that actually mean in kind of practical terms? Is it that the hardware is just not there yet, that we're spending minutes on generating proofs? Or is it that, look, we can do it a couple minutes, just the way we saw the ZK proof revolution for the last 5-6 years, and it's going to go into now sub-second or sub-100 seconds, milliseconds. And is it that phase we're part of, or we have to sort of invent new ways to think about compiling these circuits, and that's kind of the phase? So what's a good way to think about those benchmarks, or the open problems, or just overall, can we put some numbers on understanding what the scale is?
Yeah, so that's a great question. When protocols approach us about integrating FHE into their application, what we really ask them is, what is the minimum viable performance you need? So there are many cases where we can get the performance today on something that's workable with no GPUs on a 64-core machine. If people want an idea of actual numbers, we can run a first price sealed bid auction on about 64 bids with 16-bit precision in under a second time on a 64-core machine. We can compare numbers together at around 30 milliseconds as well. The main challenge, I would say, is that while those numbers are okay as of today for certain applications like dark pools, if we're willing to throw pretty beefy machines at it, it is not acceptable for anything MEV related. So some of the applications we've seen that are quite interesting have to do with block space auctions and collaborative searching. And there, the performance isn't quite what it needs to be, even on like the theory or algorithmic side. You really need GPUs, potentially even FPGAs, to get us to the final bit.
I would add to that there is, so performance-wise, there are plenty of different, subjects that could be optimized. So ultimately, for certain use cases where you need low latency, of course, hardware acceleration is like the big next thing for FHE. But there are also like things like, for instance, circuit generation. When you compile, you actually want to generate a circuit made of atomic homomorphic operations. Right now, circuit generation is a hard problem in itself. I mean, there are plenty of NP hard problems when you want to have a provably optimal circuit. But right now, it's like we have just a strategy for a number of pre-identified functions. So we have a library of strategies. We're just plugging that in, and maybe we have a little bit of optimization. But I think there's a lot of room for improvement there with badass compilation techniques that actually generate optimal circuits. There is a lot of slack in there. But yeah, as Ravital was saying, we're like missing some speed up factors for some use cases. For some other use cases, it's already usable. You can deploy. I mean, nowhere is there. But if you want to do like encrypted AI,
a lot of GPUs,
just inference. I'm not even talking about training. Even though recently we've made achievements in the field, we can now train not neural networks, but like decision trees. We kind of cracked it. So we have a first solution to that. But the smallest LLM would have like already like millions and or even like billions
of parameters by default, yeah.
And so so it's a lot of workload, and we're nowhere near approaching what you can do in terms of performances in plain text with what we have today. So we really need a hardware acceleration to achieve kind of the same, what we coined with the term, homomorphic supremacy. Homomorphic supremacy being that moment in the future where with a hardware acceleration, you kind of have the same kind of performances that non-hardware accelerate plain text equivalent computations. So by default, it's going to be FHE encrypted unless there is some, you will have as OpenAI, if you're OpenAI, you will have to justify why it's still being done in the clear. It will be suspicious because probably you want to access the data.
The HTTPS moment of working on data. Pretty good.
Expanding on the idea of this library of optimized compilations of some functions, I completely agree with that approach. And if you think about the plain text world, it just came to my mind this book at MIT, Introduction to Algorithms. And if you go through it, like there's decades of work collected in that book with the best algorithms for sorting, for searching, for graphs, for databases like binary trees. How do you insert? How do you delete? How do you find? For greedy algorithms, linear programming, and whatnot. I think in general in MPC and /FHE, we're lacking something like that. I think we have the knowledge to start writing some of the chapters of the equivalent book, because the techniques that they use there in plain text don't directly apply to kind of secret shared or privacy enhanced computations, unfortunately. So we need, in a sense, to reinvent all of that body of material, all of that knowledge. And although we can write some chapters, I think we are still a long way to being able to write a complete thick book like that, which covers like the best way to optimize and build all those different solutions to those different projects. And until we don't do that, we won't be able to write efficient compilers as in the plain text world. We're doing a great job, of course, with what we have, but I think there's plenty of room for optimization on that front.
So maybe one thing I'm kind of curious about is, does this kind of imply that the only way you can kind of get this to be more practical is just throw more hardware at it, or is it is it a bad assumption? Like, is there something should there something be wrong with that statement? Or is this the only way because we kind of saw the Pentium 1 to i7 era for the last 20 years, but this is just what it means. Now you have to think about GPUs getting more commoditized and faster and better, and this is the only way we can do this thing? Or is it kind of considered a bad thing that we have to already consider ASICs or FPGAs or more GPUs, so that means it's impractical, we're trying to make it more practical? What's a good way to think about that sort of way to introduce a technology that is very promising, but is fundamentally limited on capital here to make it more applicable?
So I guess for us, the reality is we do need this hardware to rescale, 100 at 1000x a magnitude higher. But in the meantime, there's also another idea which, you could leverage ZK, for example, combine ZK and FHE. And one example I can give is, for example, if you need to, in a game where you need to validate, let's say, a hidden move against 100 existing moves, then you can also do this off-chain using ZK and just do the state transition using FHE on-chain, right? So depending on the use case, there are also ways you could potentially leverage ZK as a way to just like offload a lot of the heavy computation validation logic. At least this is how we think. We want to be pragmatic on what are the use cases that are feasible today before hardware acceleration. And I do think ZK could provide a sweet spot for compensating for that as well. Yeah.
Yeah, and I think there's ZK is also one of these other PETs, right? But in the realm of PETs, there are plenty of citizens, right? So we've been talking about FHE and MPC. ZK is obviously, well, not one other technique, but like a pool of different techniques doing different things. But there are also plenty of others that are like, anonymous signatures, even like group signatures or things like that are not really deployed and that are like low-hanging fruits that Web 2 is not like using in any way, and that Web 3 is like could adopt like overnight if there was a use case for that. There are plenty of different solutions. I can think also of whitebox crypto, for instance. This one, in PETs, there are problems that have been cracked, and we have like reliable solutions with security proofs and the like. And there are still like fantastic dreams, like FHE was for a while, that haven't been cracked yet. But the day somebody cracks that problem, like whitebox crypto, it can be completely disruptive and transformative. Whitebox crypto meaning I can hard code private information into an executable. So I take an AES key, I put that in a software that just does an AES decryption. It's kind of obfuscation if you want, but it should be provably secure. So I can give you the executable and you will be able to perform like AES decryption or encryption, but you're not capable of finding the key that is embedded in there. And so somehow with that concept, you can achieve public key encryption with AES, for instance. You can do so much more that we can do today. So it would be another way to kind of replace secure hardware, and we wouldn't need TEs anymore. And so that would be another way of like
good feature to look forward to.
But there are plenty of ideas in this space, and but also very, very hard problems to tackle to get there.
Totally. That is a great point. It's not just a couple of problems in kind of the whole area of PETs. There is a whole set of other tools that you have, and you also can combine them, and you should, because you can't rely on one technique to kind of fully optimize. Is not the only way to get there, right? Kind of speaking of all of that, again, this kind of applies to all four of you. How do you think about the developer experience? Of course, a lot of this introduces new technology and just kind of new ways to think about it. Do you want people to kind of be thinking about everything as multiplication addition? Probably not. You already chose the route of making EVM-compatible code, just be kind of bifurcated in that sense. But kind of I'm curious about you. How do you think about working with MPCs? and kind of doing key generation and verification. And as you write your compilers, what would you like the ideal developer experience to be as well?
Yeah, I think it's a good topic and a challenging one as well, because of what I was saying before, that there is a big difference between programming in plain text, so to speak, and programming on this type of technology. So developers need training, developers need like a new way of thinking, and simple things like what happens in runtime is completely different here. Like, for example, in a developer experience from plain text, you typically run a program, it crashes. It gives you feedback as a developer that you have something wrong, so you have a bug, and to the user, if it's happening in, to the user, then they know that they cannot trust that program for whatever reason. But what do you do if you have like a division by zero, or if you have an overflow? You could add checks that kind of look for that type of situation that would have an impact on performance. But the problem is not just that. The problem is that you would be leaking information. Because if we're running a multi-party computation, and let's say I'm injecting some of the variables, I could just choose my variables to force this type of situation. And when it happens, I know some information about your variables because they were also involved in this overflow. So something as simple as runtime, which is something we take for granted, completely changes when you face it from this perspective.
I think I can build on that too. So I would agree with pretty much everything said. The experience right now with FHE is really, really far from what it should be for developers. The ideal experience would really involve a developer just writing a program in Python or Rust and us being able to effectively transform it into its private equivalent. The reality, though, is that if we take that approach, the performance is so abysmally bad, it's not usable for really anything. And what we have to do is ask the developer for help. So we have to ask them, well, which of these inputs are encrypted? What kind of security do you need? And in many cases, we can transform the programs pretty well with very few changes. But in more complex cases, say for dark pools or auctions, you really have to rethink the entire application design to get something performant.
Yeah, maybe just to add to that. So, granted, we are integrating FHE to an EVM, which makes it a lot easier for builders to build. They can also use existing tools like MetaMask, Hardhat Remix. On the application layer, I think there's another design space or like design principle that people have to be aware of, is that, for example, you cannot use if-else statements. If you have encrypted data, you use if-else statements, that will essentially leak information, right? So there are circuits like CMUX multiplexer that allows you to, do operations based on encrypted Boolean, right? If this encrypted data is true, then you run this logic or this path. If it's false, it runs this other, logic or path or ciphertext, right? And this, in a way, is something a little bit different and a little bit newer, I would say, in the crypto space, where thinking about designing confidential DeFi or games, you really have to be careful about not leaking information in a way that's not intentional, basically.
Yeah. To explore that a little bit more in detail. So as you were saying, if you do a conditional branching in a program, everybody's aware. I mean, anyone who develops, uses an if-else statement, like maybe 30% of instructions,
Probably more.
Probably more in a given program is actually a test. And fully morphic encryption contaminates everything it touches, right? So if that predicate, that bit of information depends on an encrypted input, then it's going to be encrypted as well. So you cannot decide what to do with that control flow at that moment in time where you're supposed to jump in the then body or the else body. You cannot decide. So fortunately enough, we can, if the then body is like, I assign 3 to the variable A, and the else body is I assign 7 to A. Fortunately, you can kind of regularize that portion of code into a CMUX when you were saying, I can do multiplexing. Like I take the bit that is encrypted, so it's 0, 1, but encrypted, and I assign to A 3 times the bit plus 7 minus times 1 minus the bit. And that I can do homomorphically, and there you go. You kind of transform. So in the compilation, at some point, we should also consider regularizing naive programs that are not aware of that issue, so that every if-else statement is converted automatically into linear branchless code. But fortunately enough, we kind of know how to do that. It's just not in production yet, but it's coming.
That was actually a really good explanation. But it means like now you have to give the choice that do you want to do this thing as a compiler optimization, or tell them that this concept needs to be replaced with an if-else because this is what happens and the side effects.
Yeah, exactly. But what we want ultimately is the developer experience should be, oblivious of what's happening next in the compilation process. So the developer should have like no change in the developing experience itself, or at least we're trying to get as close as possible to this vision where anyone can actually use the technology without having to know anything about it.
And from what you know now, do you believe that's possible? Or does that still mean that we will have to still introduce a handful of other kind of new concepts on kind of new paradigms, or rather just new conditionals or loops or just primitives that requires them to know specifically how that environment is?
We're kind of already there. I mean, outside of the FHE VM, we also have like Concrete Python, which is a Python front end to our compiler, Concrete. And actually you can write down like Python code. And this front end is going to convert that directly and kind of apply this topological transformation. It is just not as powerful as we would like it to be. It's getting there, but it also like sometimes very hard, to tackle all these problems at once.
It's possible, or maybe we just need time to get there.
But the experience right now is, the developer just knows Python and kind of use like encrypted data types and tags, which variables should be encrypted, and that's it. And the rest you leave to the compiler to figure out. It already works today. It's not
Well, as a last question, everybody, what can people look forward to with what you're doing with your protocols or your products, and what's kind of something you want to share with them that might be interesting to the audience on PETs?
So we're currently very interested in the problem that I mentioned before about AI, and it's a moonshot. It's a very difficult problem to tackle right now with existing technology. As Pascal was saying, we're talking about billion parameter models. But running private inference of such large language models would be very beneficial, because they would not only protect the model weights, but most importantly, the user prompts. And although it's a moonshot, there is like lower hanging fruits along that path that takes to that position. And that is, for example, retrieval augmented generation, or the fine tuning of some smaller version of that model. Those are actually the ones that will probably start manipulating personal information or private information. So it's a good way to go. And we're trying to tackle this problem from the standpoint of using a theory that is called wavelet theory. It's from digital signal processing, and applying it to this problem. And so far we are still at a preliminary stage, but we're getting some exciting results. And we hope to be able to push the limit a little bit forward to make this this technology a little bit more feasible.
We're most excited about bringing privacy to both CeFi and DeFi. We think bringing privacy there will really allow institutions and sophisticated actors to join the space en masse so that they can hide their strategy. In terms of some exciting announcements for us that are upcoming, we have been working pretty hard on the theory side of FHE. So we've managed to make some advancements there. I can't say it's what hardware is necessarily going to get us, but it certainly makes a significant difference.
Yeah, for us, we are quite excited to see what people can build on top of Inco. We really think this is going to be the next frontier for novel dApps, novel experiences, and we'll be hosting a few hackathons this year with ETHGlobal, but also other folks. And I think that's going to be the best way for developers to really get first-hand experience, is to do a hackathon. Come talk to us. We also have a lot of ideas. We can give you feedback. And just looking forward to see what people are going to build this year.
Well, for Zama is a technology enabler, right? So we're not a blockchain company. We're not an AI company. What we want to provide is, a state-of-the-art FHE tools that anyone can use. And then people have to figure out their own use case, what they want to do with it. But people are naturally very creative. People are builders. So, yeah, for us, what's coming is like improving the tooling. Everything should be simpler. Everything should be smoother, more efficient. So we're like partnering with hardware houses for hardware acceleration. And we'll probably make new announcements during the Ethereum conference this summer. So
Amazing.
Stay tuned.
A lot of cool announcements to look forward to. Well, Miguel, Ravital, Remi, and Pascal, thank you so much for joining us for this amazing discussions. And hopefully the audience has now a better understanding of PETs. Thanks.